My name is Doug Sterling. This is Frank Kish. I'm a developer and Frank is a product engineer on the network analyst team. And we are giving a talk on ArcGIS Runtime Network Analysis. First thing I just added, if you're looking for information on the utility network tools, the utility network services present in ArcGIS Pro, or if you're looking for information on the utility network tools present in the 10X software suite, this is not the talk for you. This is about network analyst functionality, vehicle routing, pedestrian routing, service areas, closest facilities, all of that within the ArcGIS Runtime SDK platform. So it's okay to leave, otherwise you'll figure this out halfway through and you're going to realize you're in the wrong spot.
Should there be any place that has
You should probably ask if the information desk.
Yeah. Okay, so the second question I have is, how many people here have any familiarity whatsoever with the ArcGIS Network Analyst product stack, either in ArcMap, ArcCatalog, Services, Pro? Okay, it's okay if you just have some familiarity. And just for our own interest, in general, what programming language, so the ArcGIS Runtime supports multiple SDKs. How many of you do development in C#? How many of you do development in Java? How many of you do development in Objective-C or Swift? How many of you do development in Android Java, which is not Linux Java? How many of you do development in Qt? Oh, tough crowd. That's why all the Qt badges are still out there. Okay, did I miss one? Xamarin? It's .NET. C#, which is .NET. Okay. What we are going to talk about, or I'm here to talk, Frank's here to demo. I'm going to talk about what the network analysis tasks are. I'm going to talk about what functionality is present in them. We're going to have some demos. For the most part, this is a high-level overview for the tasks and functionality that we have in our software. A lot of the functionality that we're going to talk about is new at the 100.2 release, which came out at the end of last year. I want to talk about what functionality is common to all of the network analyst tasks. A lot of this will look very familiar to desktop ArcObjects if you're familiar with that. We want to talk about, for programmers, what are the objects? What do they do? We just don't want to throw you at a code sample. We want to try to help you to understand why these objects exist, what they're here for, how it is that you use them. We want to talk about how things work, answering some commonly asked questions that users have asked us over the years. And we want to talk about the differences between online and local tasks. So to start off, there's the route task. This has been around for a very long time. It's been present for the 100 and the 10 release of the Runtime SDKs as both an online and a local route task. It does, for the most part, a lot of what you think it would do. You can generate a route between a set of stops, 2 or more stops. You can generate driving directions, and the most common use cases are for navigation, they're for route optimization, they're for basically figuring out how you want to get between a collection of points. You can take a fixed sequence of stops and generate the route between them. You can ask the route task to find an optimal path between a collection of stops. So you can say, I want to start my day at the depot, I want to end my day at the depot, but here's all the stops I have to visit. You tell me what the optimal path is. And so as we can see here, we're getting a somewhat more sensible path where we start at our depot on the left-hand side and move around. And you can optionally preserve the first or last stop. You don't have to do that. Another thing that it does is it supports the concept of time. So here we introduce time windows to our stops. So we're saying you can't just visit this stop to make a pickup or a delivery whenever you want. You have to show up between a certain time. And so if we look at the route here, what happens is we leave our depot at 8 in the morning on the left-hand side, and then we drive past what will turn out to be stop number 7 and 6. And we head over to the right, pick up those stops, and then once the time is correct, we head over to stops 6 and 7, because we were told the problem, you can't visit these stops until a certain period of time has come, because the person won't be there, they're not ready for you, for whatever reason. So these are all just some very high level, very general descriptions of what the route task can do, but what's way more exciting than PowerPoint slides is an actual demo. So we'll pass this over to Frank. We're going to be we only have one HDMI plug, so we're going to be doing a lot of hot swapping today. It's like a pit crew. All right, and here we go.
All right. Okay, so Doug was telling you about the route task, and I'm just going to show a short demo on some of the functionality. So for one, we can actually, what we're looking at here is just a map of the world. So it's just an ArcGIS online map. And what I'm going to do is just do routing through service. So the first thing I need to do is authenticate, because right now I'm going to use this world geocoding service that's going to require a login, and it's going to use credits for me to route. So if I just zoom into an area, that might be easier. So if I just zoom into an area, I can just drop a couple points, just randomly in this case, and then solve using the online solver. What I get back is this particular route, and I can get some information off that route. So we can see up here we have a travel mode. That's a property of the network data set that Doug will probably mention later on. The impedance that's being used for that particular travel mode, and then a couple other things like the total length and total time for that particular route. I can also get directions back. So if I look at these directions, we get this text, and it's more than just text because it actually has geometry, so I can move through this. And if you look at the object model for this particular, for our API, you can see that there's more things that you can get off the directions when they come back. So that was using online services. Now, we can also do local. So I'm just going to load this mobile map package. This is a StreetMap premium data set that we have, and it's of California, and it's an MMPK. So that stands for mobile map package, and it's something that you could create in Pro. This is California, so we'll just see this is the package that you, or the area that you get for California. So if I zoom back into this Redlands area, one of the things I can do is I can load some stops, or in this case I called them work orders. And these stops are coming in actually from an ArcGIS service, and I'm just creating points or point locations for them. And then I can use those actually to just do my solve using the local data now, because this mobile map package actually has a network data set embedded in it. If we look, we can see that the first stop is here in green, and then we go over to the second stop, and then back here to the third stop. So in this particular case, we're not doing any optimization. We see it takes it's 105 miles and takes 2 hours and 30 minutes. Now, one of the things you can do is just say, find best sequence, and that's just a Boolean flag. And in this case, I'm going to say preserve first stop, because this is my beginning point of where everyone comes out of for the beginning of the day, let's say. So we go from 105 miles and 2 hours and 30. And if we do a solve using the find best sequence on, we get a much more sensible route. So we go from 2 to 3 to 4 in a more appropriate manner, and we drop down to 44 miles and an hour and 23 minutes. So using something very simple, a Boolean flag, and letting your solver decide the best path can save a lot of time. And I think that's it for now regarding the route task. There you go.
I almost plugged HDMI into USB. I don't think it works very well. I gotta switch my monitor. Okay, up next is the closest facility task. This is something that's been present in the 100 version of the ArcGIS Runtime SDKs, which came out over a year ago, but is present in the 100.2 version, which is just released for local data. Most commonly, it's used to find routes between incidents and facilities. The most common use cases are if you want to find the closest bank, or if you want to find the 5 closest fire stations to a location, or if you want to find the closest ambulance to a location. This picture here is the squares represent people, maybe their cars, maybe their houses, And the circles in this particular case are actually Wells Fargo bank locations. And so what we're doing is for each of these squares, we're finding the two closest Wells Fargo bank locations. More interestingly, the number of routes that you get back can be constrained by a number defined and also a cutoff. So you can say something like, I want to find up to 3 stores, but I don't want to search any further than 5 minutes out. And routes can go either from the incident to the facility, or they can go from a facility to the incident. So, for example, if you're routing a fire truck to an accident, that's kind of like a facility to incident type problem. And if you're routing, the ambulance from the accident to the hospital, that's an incident to a facility type problem. And as we'll talk more later, routes can either arrive or depart at a specific time of day. So you can say, hey, I'm leaving at 8 a.m. Or you can say, I want to arrive at 8 a.m. Can you tell me when I should leave? For the ArcGIS Runtime Closest Facility task, another use case that it is used for that in the traditional desktop or ArcObjects platforms, you had a dedicated solver for this, was to generate a matrix of costs. So don't be confused by the picture here. I just rendered the route shapes with a straight line. We are actually traversing the graph. We're not doing anything with Euclidean distance. But if most common use case for this is you have a collection of coincident origins and destinations, in this case facilities and incidents, and you want to find the cost from everything to reach everything. Usually this is a precursor to some kind of dedicated home-built optimization logic. For example, internally in the route task, when we say, hey, let's find the best sequence of stops, the best sequence of stops to visit, the first thing we have to do is find the cost for every stop to reach every other stop, and then we, from that matrix, find out what is the optimal path. So now back to Frank.
Again, I've just got another map and I'm using local data. So what I'm going to do is I'm going to drop a couple I'm going to drop a couple instance that I'm creating here in green dots, and then I'm going to put on a couple of facilities, and then I'm just going to solve. So what's that going to give me? That's going to bring me back one facility for one instant. And I could cycle through these and see what they are. I also get directions back if I solve on it with directions. I didn't put that in. So then the other thing that Doug had mentioned is the fact that you can change your facility count and your cutoff. So let's say I want to actually find 2 facility counts for each of the instance. So I can solve. And now we see we get back multiple routes to multiple facilities for each of the instance. One of the other things I can do is set an impedance cutoff time. So we see that the time here is from about 8 minutes to about 11 minutes. Let's say for sake of argument that I only want to have anything under 10 minutes. So I can put a cutoff of 10 minutes. And now I expect a couple of these to drop out. So now if I do a solve, we see that a couple of instances or routes have dropped out. So even though I'm asking for 2 for each, I don't always get that back based upon my impedance cutoff. Fairly simple. And back to you, Doug.
Okay, up next, my favorite task. I love them all. The surface area task. I wrote them all. The surface area task is used to find the area that can be reached by a facility or multiple facilities. So in this picture here, we have a facility, it's the circle in the middle, and we're finding the area that can be reached within 2, 4, 6, 8, and 10 minutes of driving time. The most common use cases, first and foremost, visualization. If you want to say, here, where's my fire station coverage? And you want to visually see it and say, oh, look, there's a hole in the middle. We have a new subdivision. Maybe it needs a new fire station. More interesting use cases can be to pre-compute reach. for your facilities. So, for example, you go to all of your bank locations, generate 10 service areas for each one, load it into a spatially enabled database, and then instead of performing network queries, you could just perform raw spatial queries against the database to say, hey, which polygon did my customer address point land in? Because that's going to tell me about how far they are. And it can be as accurate as you want. It can be down to the half minute, minute, quarter minute, or 5 minutes. It's up to you. Other things that are coming at the 100.3 release, which is not yet released, we are going to expose a higher level of quality for the polygons. So what you have on the left is what's present for the local service area task in the 100.2 release. And what you have on the right is what we will have as an option in the 100.3 release. And the difference is that we have a higher quality setting. The setting is already there. It's just not fully enabled in the 100.2 release, where we will perform a space filling function between what is traversed and what is not traversed. This is really useful for fire stations, for other things. Most people usually like the polygon on the left. It's a bit simpler to understand, and they're not quite as interested in the fact that there are walkable paths, or there are, for example, like gravel driveways or dirt roads that are causing holes in their polygons. Some people love the ones on the right. Most people love the ones on the left. You can choose which one you want. Also, with the service area task, you have the option to return the lines that are actually traversed within your cutoff. So in this case, this is the exact same output as the previous solve. It's just these are the actual lines that are traversed. You can, for each of those lines, accumulate the time it takes to reach the beginning and the end. You can accumulate the distance it took to reach the beginning and the end, whatever attributes you want to have on that. And back to Frank.
So again, we're looking at an area around Los Angeles. I'm going to show you a couple things about surface area. If I just drop a point, it's going to default and give me a surface area for 5 minutes. I can establish some other cutoffs and just solve again, and now I get 5 and 10 minute cutoffs, so you can expand that out. As Doug mentioned, you can return polylines. So if I solve here, might take a second longer because it's bringing back a fair bit of lines. If we're, especially downtown Los Angeles, there's a lot of roads. But for the most part, it's actually a fairly. I'm going to set up a continuous solve, so it's actually pretty quick when we're doing solves in the runtime. So I'm just following my mouse and making service areas as I move through the actual feature set. So pretty simple, but pretty powerful.
Okay, so these are tasks. They all do different things. There are pieces of functionality that are common between all of the tasks in the runtime framework for the network analyst tasks. First and foremost, the most common part between all these tasks that Frank has been demoing is that the programming patterns are the same. For the most part, with very few exceptions, all the tasks work with online services as well as with local data. And there's the same programming pattern for consuming them. And the only difference is when you create the task object, you basically specify, is this going to talk to a URL, which is a service, or is it going to talk to local data? Once you've done that, once you've created the task, programming against them is identical. So there's really not much of a difference between programming for an online service versus programming for local mobile map package data. And you've seen that in Frank's demo, where he has his nice C# app, and he's been able to seamlessly switch over and say, oh, instead of solving against the online service, I want to solve against local data, and he just presses a button. There's no other code changes. All it's doing is just creating another task and feeding it off to the logic that he wrote, and it treats it the same regardless of whether or not it comes from a service or whether or not it comes from local data. So it's a very powerful piece of, it's very powerful, it's very useful to know. It makes it very easy to write applications that can talk primarily to a service or fall back to local data or vice versa. Another piece of common task functionality is that all of the network analyst tasks are time enabled. The route task, it can have a start time. You can say I'm leaving at 8 in the morning. You can say that stops have time windows. I need to visit this house between 9 and 10 in the morning and that house between 10 and 11 in the morning. The closest facility task, you can specify a departure or an arrival time. And also for the service area task, you can specify a departure or an arrival time. So you can calculate the area that I can reach within 5 minutes. That's more of like a fire station type scenario, like where can I get to? Or if you're a business, you can say, well, who can reach me within 5 minutes? That's more of like a department store scenario or a business scenario. Another piece of common functionality to all the tasks is that they take barriers. Again, this is, if you've used Desktop Network Analyst, this is basically the same thing. Barriers can be point barriers that restrict a particular location, or they can be line barriers that restrict everything that they cross, or they can be polygon barriers where they'll restrict everything that they have an intersection with. So I believe for Frank's final demo and the final passing of the HDMI cable, we're going to get a demonstration of barriers and time.
So again, I've just I'm zoomed into the Los Angeles area, and I've dropped a couple points here, one in Los Angeles, one in Anaheim. If I do a local solve, we see that we get back kind of almost 31 miles and about 50 minutes. So one of the things I can do is I can bring in some cost barriers. Right now I'm bringing in this this cost barrier here that's a scaled cost barrier. It's going to increase the cost of traveling through the edges in this area by, I think it's an attribute on the polygon itself, and I think it's like set at 3.5. So once I solve with that, we see we went from 51 minutes to 55 minutes. So that's caused by this increased cost of going through this area. The other thing I can do is I can add a restriction barrier. This is coming from a polygon from ArcGIS Online. And basically it's going to say you can't go through this area. And now if I solve on that, we see that the actual route completely avoids that. In terms of time, fairly simple demo. I'm just going to drop a point, and I'm going to solve a service area that's 10 minutes for 8 a.m. And we see that we go out that distance. And then at 4 p.m., we can see there's a fairly big difference between using one time versus the other. And that's based upon, in this case, historic traffic, because it's now it knows its start time, and it can understand that 8 a.m. has less traffic in Los Angeles area here versus at 4 p.m. Back to Doug.
Okay, so this is a developer conference. This is a code sample. This is the simplest task sample that we came up with, and it is that we would like to generate a service area polygon. So it's written in C#, and if we got it right, it's Frank's doing, not mine, except for one line that I wrote, and I hope I got that right. So if you find a bug, it's Frank's doing. The first line, we just create the task. As you can see here in the creation function, we're passing in a URL to a service, so that's an indication that this is an online task. The second line, we just create a parameters object for our service area task. Third line, we create in one very verbose line of code, we create a service area facility from a point, and we put that onto the facilities property of the parameters. In the fourth line, we actually do the solving right here. That's where all the fun happens. And in the fifth line, we basically just fetch our polygon out from the 0th facility, which is the only facility we actually put in. So in terms of code, it's not too complex, but what are these objects doing? This is where the talk is going to veer a little bit more over to probably what developers are interested in. What's the purpose of these objects? What do they do? How do you use them? How do they work together? Because you'll see this pattern for any of the code samples for any of the tasks. Create the task, create parameters, set options on the parameters, solve using the parameters, and then get your results. So taking a step back, the network analyst tasks have a pattern. It doesn't matter which SDK you're using. It doesn't matter if it's .NET. It doesn't matter if it's Objective-C. Doesn't matter if it's Java, they have a pattern where you can follow them. And these are at a very high level what the objects look like, and the pattern is to start here on the left and work your way over to the right. So what we're going to do is I want to talk pretty quickly about each of these just to give you an idea of why they're there. And we'll go back to that slide if you want to take pictures. So tasks. There are 3 tasks. There's the route closest facility and service area tasks. Objects that perform network analysis operations, that's what the tasks are for us. There are other tasks in the software stack for runtime. It's not as though only network analyst has tasks. Tasks are objects that can be created as needed, or they can be created and reused. It's not like once you solve on them once, you have to throw them away and recreate them. In Frank's C# example, he actually will create 2 tasks. He'll have one for local solves, one for online solves, and he just passes them around. Tasks have to be loaded before being used because they can have to talk to potentially a service. That's why if you look at the SDKs, they have an asynchronous load method, like an asynchronous creation method. If you're ever wondering, like, why do I have to await on creating a task? It's because it has to go talk to the online service to make sure that it exists. Task solving takes place on an internal thread. So if you're on an iPhone and you basically say, I want to wait on this thread, internally in Runtime Core, we spawn another thread that actually does the work. And tasks can actually solve multiple problems at once. This is an interesting point. If you want to solve multiple routes simultaneously, you can actually feed them one at a time to the task operation, and we will clone your inputs before we pass flow of control back to you. And tasks for online services or local data, they can be for one or the other, but they can't be changed once they're loaded. And nobody here uses Qt, but that's okay. I'm sure somebody is somewhere. And all the SDKs, this is really obvious because there's one way to construct them, but for the Qt SDK, you can actually set it up to be either way, and once it loads, it's locked in place, and if you try changing it, you'll get an error. Up next, what I want to talk about is this task info object. So task infos are obtained from loaded tasks. They can't be created. So you can't create a task info object on your own. It describes the default state of the task. It describes the travel modes that are available to you, either that the service is set up or that were built into the local data. It describes the available cost attributes and restriction attributes that are supported. It describes the default spatial reference of the data. Maybe it's some custom coordinate system. And also has an awful lot of task-specific details. So for example, by default, does the service find the best sequence of route stops? Or by default, does the closest facility task go from incident to facility or from facility to incident? This is, if you want to reset your inputs, you would usually go to a parameter object and say either recreate it, or you could one at a time repopulate them using the task info. Up next is the travel mode object. Now, the travel mode object is an idea that is represented across our software stack. It's present in ArcPy, it's present in the online services, it's present in runtime, it's present in desktop ArcGIS. And it's basically a way of interpreting a network data set or a transportation network in a mobile map package according to some means of transportation. So driving a car versus driving a truck. Cars probably can go more places than trucks can go. There might be height restrictions. Another good example would be rural driving a car versus driving a car. In a rural environment, you're more willing to drive on unpaved dirt or gravel roads. Increasingly, something that's very common is that people will create travel modes for specific kinds of vehicles for a police car versus a fire truck. If you're a delivery company and you have, one size of delivery vehicle, you might make a travel mode specifically for that vehicle versus for, say, a semi-truck. Maybe they have different turning radiuses. They might accelerate differently. They might have different top speeds on the vehicles. And travel modes as objects contain the impedance attribute that we use when traversing a network. So are we minimizing the time it takes to get between locations, or are we minimizing the distance taken, or are we minimizing some other attribute? It could be a dollar figure. I want to find the literal least cost path between 2 points. It contains restriction attributes. Are we going to honor one way, or are we not going to honor one way? I'd recommend honoring one way unless, you're an ambulance. I've seen plenty of ambulances driving on the wrong side of the road, but I don't think they do it for long stretches. And most importantly for the online services, but also very much so for runtime, is this point that it describes where it is that we can locate inputs. So we'll talk a lot about this later because we are always given lots of questions about how do you know where to locate stops or where to locate facilities or incidents. And the travel mode plays a very large part in this. Travel modes, this object, you can programmatically create it. Everything you need is there. But what we most commonly recommend is that people create them as part of the desktop GIS process, that they play with it there, that they test it there, that they get it working in the desktop application and make sure it's what they want. And then when you export your network data set into a mobile map package, it just kind of comes along. But if you want to, you can programmatically create them. Up next, parameters objects. Parameters are really, for the most part, just collections of task settings. Do you want directions or do you not want directions? Do you want to have no route shape geometry? Do you want to have a straight line route shape geometry? Do you want to have a route shape geometry that actually follows the exact path of the streets? Do you want to get barriers back in the solve or not? Just every input that you can think of to our solvers, it's present in the parameters objects. Parameters are also collections of task inputs. So this is where your stops are put, where your facilities, incidents, service area facilities, point, line, and polygon barriers, that's where they're put. These inputs can either be objects, that's perfectly fine. You can create programmatically a stop object, give it a geometry, put its attributes on it. Or it can actually say, you can say, I want to load my stops from some table over here. So within the runtime framework, you can say, this is my ArcGIS feature table, and it could either be local or remote. I want to pull my stops in from it. Parameters are used by the task objects when the task is solved. And you can create a parameters object if you want, or you can go to the task and ask it to create a default parameters object with whatever default settings your network or your service was published with. And as I mentioned before, when you pass a parameters object into the task for solving, we clone it internally. So once it comes back to you, you can recycle that parameter object. You could put different stops on it. You could send it back to the task and solve again. Up next, inputs. All inputs require a geometry in their constructors. And the geometries are all points. So facilities, stops, incidents, they're just all points. They can all specify which side of the street they either have to arrive or depart from. So you can say, you need to approach me, you need to arrive at the right-hand side of the street. They can have an added cost, which is used to model what happens in the real world. So you can say this stop takes 5 minutes to service, but this stop over here takes 10 minutes to service because they have an angry dog and it takes the owner time to put the dog in, the shed. You can model facility departure time. So for service area, what's commonly called shoot time, which is the time it takes to get the fire truck onto the road. You could say this facility, they're quick. They sleep in the fire truck. They're out in 10 seconds. And that facility, they sleep in tents in the back. It takes them 45 seconds. So they're not going to get going as quickly. Inputs can have properties that are very specific to their task. Some properties are set actually by the task itself. So for the route for the route task, when you get a stop back from it, we'll say, well, this is the sequence of the stop. It was the 5th stop visited, or we arrived at 9:30 p.m. and we left at 9:35 p.m. And also we'll tell you where it is that we located on the network and what the location status was. Up next, barriers. Again, all barriers require geometry in their constructors. It's all based on geometry. And they can do one of two things. First of all, they can just prevent inputs from locating on a portion of the network. So if you say, there's a parade here, this street, it's closed off, or maybe it's flooded, it's just not accessible, and you put a stop into it, we will not actually locate the stop on the street in the flood zone or in the parade. What we will do is, and we'll talk more about this later on, we'll locate it somewhere nearby that's traversable. They can restrict traversal for a point, polyline, or polygon geometry. Optionally, if you want to, you can use them to model added costs. So say you have like a checkpoint that you may or may not want to drive through. And we saw this in Frank's demo where we took a section of the 5 freeway and said, it's just slower. There's, something has happened here today. It's a temporary thing. Let's slow it down by 3.5 times, which, I know that section of the 5 freeway. It's like you're doing like 10 miles an hour if you're lucky normally. So you can say, let's slow it down, or let's just add an added cost. So to traverse this point, either you can't do it, or it takes an extra minute, to traverse this area, either you can't do it or it's going to take 2 or 3 times longer. It's up to you to set those parameters. But it's supported. That's the important point. Finally, results. Tasks take parameters, they solve them, and they give you back result objects. Result objects can contain multiple results. I should probably blame myself for writing that. But the route result can contain multiple routes. The surface area can contain an awful lot of polygons, and don't even get going on lines. It's very easy to return millions of lines back from a surface area solve. And the closest facility can contain multiple routes. The surface area and closest facility tasks, the results are enumerated by your facilities. So we always give you back your facilities and the results. And you get back a copy of the facilities. So what we want to move on to is, behind the scenes how things work. And one of the things that always comes up with regularity for both the Runtime 10x SDK and the 100 SDK is how do you locate points? Well, for the online tasks, it's not up to us. It's really how is the service configured? What were the specific options that were checked on the service? What version of ArcGIS server is it? Is it 10.1? Is it 10.2? Or is it 10.6? There could be differences between the different server versions. For local tasks, though, we will always locate your inputs on routable elements in the network. And the travel mode is what determines what's routable. So if you are a walking travel mode and you click right on top of a limited access freeway, it's not permissible for you to walk there. We will not locate you on that freeway, even though it's the closest geometric element. We will find the next acceptable element over. So you'll probably locate 1 street over. Internally, the local task will search up to 20 kilometers when locating inputs. If that's not enough, I'd love to know what your use case is, because it's pretty large. As a side note, in the 10.x version of the SDK, the search distance was infinite. And that had some interesting behavior, but there's a reason. So we went to 20 kilometers, which is also, in case you're curious, the default for ArcGIS.com. When things aren't located, usually one of the most common reasons is either your geometry is bad, or you've set the wrong spatial reference. So you, for example, given us coordinates in like a geographic coordinate system, but you say it's in like a web Mercator. And so it basically goes to like 0, 0, and it's hanging out by Africa. So that's one of the most common problems. If you've made your own travel mode, you might have accidentally restricted everything by saying all these things are restricted and we can't actually find something to locate on 20 kilometers. If you're playing around with where clauses in your data, and you'll see those when you look at the parameters objects, you might have accidentally made everything in your underlying data set restricted and you can't locate on anything. And another point that's is different from the 10.x series of SDK is new to the 100 is that if you give us an input that is very, 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 very close to a junction, it's within the spatial precision of your data, we will actually locate it on the junction. The 10x version of the SDK didn't do this. For the most part, you have to give us a geometry that is coincident with your junction to get it to locate on a junction. But if you do that, we will locate you on the junction. Other than that, we always locate you on edges. Since in the real world, most things happen at edges. Going on with locating. Local tasks will inform you when the spatially closest network element was not routable. You'll get a status of, I located you, but I'm not on the closest element. And that's kind of a hint that the closest element was restricted for some reason. It could be a barrier, maybe it's not traversable. Apps can consume this value and do whatever they want to do with it. So you can tell a driver, hey, heads up, you might want to try to figure out where this place is located. I'm routing you to here, but this location is 100 meters away from the point I was given. It's up to the app to deal with that. Another thing to know is that, and this is true across all of our software, that curve approach can be flipped if the input is not reachable. So for curve approach, if you can imagine you're in the business of delivering industrial refrigerators. You might say, let's always, in America, we drive on the right-hand side of the road. Let's deliver on the right-hand side so we don't have to cross the street. By the way, that's great. I would not want to see you, take your industrial refrigerator across the street. But in some cases, if, say, for example, it's a one-way street and the business is located on the left-hand side of the street, it's not possible for you actually to reach it from the right-hand side of the street. Internally, we catch this case and we'll flip your curb approach, make it approachable from the left-hand side of the street. And we do that, by the way, in our desktop software as well. It's not like a runtime behavior. And finally, for local tasks and also for ArcGIS Pro, we return the distance to the network location in meters. So we'll actually tell you once we locate something, hey, we located 50 meters away or 5 meters away, 100 meters away. It's really up to app developers to consume that and to do something interesting. You know, if you notice that for some reason, if we go back to like that parade example, you say, hey, you've got to make a delivery here. By the way, there's a parade and it's a disaster. You can't park anywhere nearby. We'll locate that point, not in the polygon that's restricted, not inside that barrier polygon. We'll say, well, we're routing you to over here, but this point is, 150 meters away from where the point that you gave us. That's kind of a hint that you might want to tell the driver to like, something's up. You got to look at this. You got to figure out what's going on. Barriers. There's lots of intelligence in locating stops and facilities and incidents and service area facilities. There is none of that intelligence for the most part in locating barriers. Barrier locating is purely spatial. For points, we find the nearest edge. It doesn't matter if it's restricted or not. Point barriers, like inputs, we'll search 20 kilometers to put that barrier somewhere. If you want more than 20 kilometers, let me know. Right now, it's just hard-coded to 20,000 meters. If you've got a use case, let us know. Polyline barriers apply to all edges and junctions that intersect the polyline. And polygon barriers apply to all edges, junctions that they contain, and also that cross into them. So if you have an edge that crosses into a polygon barrier, the part that's outside the polygon is routable and is traversable, but the part that's inside may be restricted or just may have a scaled cost. Unlike stops, it's always acceptable to have unlocated point barriers. It's also perfectly fine to have polyline or polygon barriers that actually don't intersect anything. That's okay. And one of the reasons for that is you might be pulling your barriers down from a feature service like Frank was. What if your mobile map package is for a clipped out area and you're pulling, polygons from some online service? Well, those polygons might not intersect with anything in your network. And that's okay. That's fine. Since there's nothing, they can't influence your network, we're just going to silently pass over them. Unlocated inputs. For the route task, if you have stops that cannot be located, you will get an error. The task will fail. And in the messages, you will find out which stop was not located, or which multiple stops were not located. We work pretty hard to locate them, so that should be an error that you encounter pretty infrequently, unless for some reason, as I said, you got the spatial reference wrong, or you have a clipped network and you're just taking things from way too far away. For the online task, the solve succeeds if there's 2 or more located stops, and unlocated stops will have a status of not located. For closest facility and service area, if the facilities or instance can't be located, the local task will succeed. Those inputs that were not located will just have a status of not located. For the online task, it's a little bit more interesting in that the solve will succeed unless there's no result, in which case it will fail. So there's a little bit of a difference in the behaviors there. Another thing we get asked kind of regularly about, as I said, on the parameters objects, you can load your stops, your facilities, your inputs. You can load them from tables. Parameters objects, they accept inputs as ArcGIS feature table objects, and that could either be a local table or it could refer to a remote table. It's just the same object. It covers both cases. The table contents are, when are they loaded? We get that a lot. They're actually not loaded when you set the table on the parameters object. They're loaded when you call solve. And there are reasons for that, mostly because we didn't want to make an asynchronous set tables on the parameters object. We didn't want to make you wait for it. Online routing service with online table of inputs. This is an interesting case that it can happen with all the other tasks as well. But if you have an online service and an online table, we actually refer the table to the service. We don't load it locally. We tell the service, hey, why don't you go look at this table? What that means is that the service has to have access to see the table. Most of the time, this is fine because they're actually the same machine. You have your network analyst server instance running on the same machine that's hosting your table data. So it's quite a boon. The data is local to the server, but if for some reason you're mixing and matching your tables, online tables with your services, pull from tables that are actually publicly visible. And input objects have properties that can be populated by field mappings. I'm not going to spend too much time on this. We get asked, well, how do you map the field names? So you have this table, has a schema, has field names. How do you figure out which field values to put into which properties of a stop or a facility or an instant? The easiest way is just to fire up ArcGIS Desktop Pro or Map, create a route or closest facility layer, and it will create those tables for you. You can actually see how it formates all the table names. We're not doing anything particularly different or new than what the desktop software has done for some time. And the final cautionary tale is that if you're loading data from tables and it has network location fields, you need to make sure those network location fields were calculated against the same data set as what you're solving against. Otherwise, they can locate in completely erratic places on the network. Although, in runtime for the local tasks, if the places that are erratic in the network don't exist, we'll fall back to the geometry and relocate them for you, because we're trying to help. Other things that work, memory. I remember the old, my first computer had 16 kilobytes of RAM. Things have gotten better since then. Actually, true story, it had such a small, it was a VIC-20, Commodore VIC-20, had such a small amount of RAM, I couldn't use the disk drive. I had to use a tape drive, which is a cassette tape drive. So things are better nowadays. My phone's got like 3 gigs of RAM. Everything that we do is in memory, though. So we do not page anything to disk. This is done for performance reasons. And as developers, just be aware that something that works on a desktop environment might not work on a phone. The big offenders are service area lines. It's very easy. If you just put a point in LA and say, hey, give me half an hour worth of lines to get back 500,000 lines. We store all of it in RAM. We're not paging it to disk. If you want to return thousands of closest facility routes, we're storing all of it, directions included. It's all in RAM. We're not paging to disk. This is fine for desktop machines. This is fine for modern computers. If you're making a home-built GIS app for a phone, just be aware of your limits. Modern phones, modern iPhones, you can allocate a little bit over 2 gigabytes of RAM before the app just goes down. And by a little bit over 2 gigabytes, I mean very little. Local task results as inputs. So if you look at the object model diagram, if you look at the result objects, you can get copies of your inputs. You can get copies of your stops back. You can get copies of your barriers back. All of your inputs, you can either optionally or as a required part of the solve, get copies of them back. If you take these inputs and you solve again, you can actually bypass a lot of work. So a good example is we had a client who wanted to, for a particular county, know that they could find the 5 closest fire stations, and I think the requirement was 2 seconds. And being a developer, I wanted to solve the problem thoroughly, so what I did is I basically selected every street in their county, and I loaded their fire stations as inputs, and I said, hey, for every street, just find the closest 5 and tell me how long it took. And it solved pretty unfailingly in about 200 to 250 milliseconds. It was pretty quick. But they had about a little under 300 facilities, a little under 300 fire stations. So what I did was I took copies of those facilities from the closest facility task. The first time I solved, I took those result facilities because now they've been spatially located. I know where they're at on the network. And for all subsequent solves, I fed those back in, and the solve time dropped in half because I could bypass 200 some spatial queries trying to find where everything was located again. In the same way for polygon barriers, the first time you solve, we have to take that polygon, spatially query the underlying SQLite geodatabase, find all the geometries that intersect. We cache all that information on the result polygon object. If you're doing a lot of operations with barriers, it's worth considering. You don't have to. Believe me, you don't have to do this. You can completely ignore this if you want. But if you want to, you can feed those result objects back into any subsequent solve, and we'll skip the whole spatial querying process, and it can speed things up. After a solve, point inputs have a populated network location. It basically tells you where exactly on the network they're at. You see, if you ever look at the tables in desktop software, you'll see the same thing. Even, the names are the same. It's like, what table am I on? What object ID am I on? How far along am I? What side of the street am I at? And you can see all that information. Something that's important to understand is that if you change your travel mode, so say you say, hey, I want to go visit this location, and I'm going to drive there, it might locate on one street. And if you take that, say it's a stop, you take that and you want to resolve with it. But say, instead of driving there, I want to walk there. Well, you probably can't walk on that street. When you take that input and you reuse it, we'll catch that it's not routable. And what we'll do is we'll relocate it for you. So you don't have to worry if I toggle some of the settings of my network or if I change the parameters of my problem, can I reuse my inputs? Yes, you can. The only thing you do need to worry about is that make sure you're solving on the same transportation network. So don't swap these, don't swap stops that are result objects between transportation networks because those network location fields, again, can produce erratic results. I worked hard to make this slide simple. Licensing. Actually, I work hard to implement licensing. So depending on what you want to do, this will tell you what you need for licenses. If you want local or online routing, online closest facility task, and the online service area task, all you need is a light license. So with a light license, if you already have ArcGIS Server installed, you can, for your SDK, conveniently and nicely talk to your server, your own server installation. That all you need is light, the minimum license level. Also for local routing, all you need is a light license. If you want to use the local closest facility and the local service area, if you want to use those tasks, you need either a standard or an advanced license, and you also need an analysis license. And finally, if you want to use StreetMap Premium data with any local task, whether it's route, closest facility, or service area, you need to get a license for that region of your data. So if I want to generate service area polygons on local data with StreetMap Premium, I need a StreetMap Premium license, I need an analysis license, and I need either a standard or an advanced license. So that's what you need for licensing. Speaking of StreetMap Premium, what is it? Well, as I said, it requires its own license. StreetMap Premium data is a data product that Esri provides. It's built using HERE data. HERE is like TomTom, except they're called HERE. It's not, I don't like the name too much. I wasn't a fan of it. But the data is actually quite good. It's high quality data for both routing, for network analyst operations, and also for geocoding. Many of their countries have historical speed profiles. So for example, they know that, as Frank demonstrated, this street is fast in the morning but slow in the evening, or maybe it's slow in the morning and fast in the evening, and that can influence your analysis when you use time. These data sets already have commonly used travel modes already defined: driving a car, driving a truck, rural driving a car, rural driving a truck, walking, and something else that I'm forgetting. Is there another? It's the same, but if you want to know what travel modes are there, it's what we use in our own online services. We actually use here StreetMap Premium data. So we use our own data product in our own online services. So the default travel modes that you see in ArcGIS.com are actually the travel modes that are just built into the data. And you can purchase it for individual states, for groups of states, for countries, or actually for entire regions. So if you want to, you could purchase like all of North America. So finally, we wanted to talk about, although the programming patterns are the same for online and local tasks, there are some differences to be aware of. For example, error messages can be different. Locating can be different for online tasks. It really depends on how the service was set up. We don't have control over that. It's really what version of server, how is the layer published. We don't have control over that on our side of stuff. We just issue the REST request and wait for it. The online route task can return partial routes if some stops can't be reached. Sometimes the route you get back, though, maybe it's what you want, maybe it's not quite what you want. For service area, depending on what version of the server you're using and what data, how it's been configured, the polygon quality can look different. And the local task doesn't support the generalized quality level. That's the hierarchical version of the algorithm. We don't support that in runtime. And what we do is we actually just upgrade your quality one level, so it's like a freebie. We don't support it, but you get something for free. Local tasks use transportation networks directly. Transportation network is what you get when you publish a network data set in ArcGIS Pro inside of the mobile map package. If you were to open it up, and take a look at it, you'd see the SQLite geodatabase, and hanging out next to that would actually be a bunch of binary files which house your transportation network. Let's see. Default parameter objects can be different between, again, it goes back to how your service was set up. Even if the data sets are the same, they could have different default parameters. It really depends on how your service is set up. These are just things to know in case you're curious to program simultaneously for both local and remote. Other differences, online network data sets support script evaluators. There's no VB script in iOS and Linux and Android. Yeah, it's just not there. So if you have a network data set with script evaluators, you won't be able to publish that. New for support for the 100.2 release was the global turn delay evaluator. So that is now supported inside of the runtime solvers, or the runtime tasks. And local tasks do not support live traffic. They do support historical traffic patterns, though. Online tasks do not return the input distance to the network. So if you locate a point, it won't tell you how far the input geometry that you gave was from where it actually located it. That might be coming at some point in time in the future. Online tasks do not return when inputs are on the closest element that is not restricted. So it just says, hey, I'm located. It doesn't say, well, I'm located, but the closest element was restricted, so I had to move you over. It doesn't give you that as input. And that's really all we have. Are there any questions? Yes?
When you were doing the time differences with service areas, were you calling the service area twice, or was that roundabout?
No, I called it twice. I called it once by setting the start time as 8 a.m. and then a second time with.
Because I'm through Python, I'm creating a service areas table.
Mm-hmm.
So I want to put times in there.
Yeah.
What do you think is best? Like twice a day, 4 times a day, or what would be the best time frame for that?
Depending kind of what you want to do for site suitability analysis, I would sit down and say, when do people use my service? So if it's a Starbucks, I guess, 7 in the morning, 8 in the morning, but definitely not like, I don't know, maybe 3 in the afternoon. But I mean, mostly I've seen Starbucks lines, it's in the morning. If it's a fire station, I mean, fires happen all times of the day. Fire trucks are a bit odd though, because they get right of way wherever they go.
It's trash trucks.
Okay.
But they're taking material at all times of day
Mm-hmm.
to the closest facility, or they first determine if the facility they want to go to takes the kind of material that they have.
Yeah.
And then based on that, they want to go to the one that takes less time. But it could be a lot longer to one in the afternoon than it is in the morning.
You don't have to solve with time. You can solve, excuse me, using a time. If you don't specify a time, assuming your data set is enabled for time, we'll fall back to a time neutral attribute, which is a more generic travel time it takes to traverse the edge. And that would be what I would do if I didn't know when I was going to be going to the depot. So you don't have to specify the exact time of day for any of the solvers. You can actually ignore time completely. And you can say, show me where I can get to 5 minutes, not telling it the time, it's kind of generically where can I get to in 5 minutes. And depending on your data set, where it's from and how it's built, that could either be just using posted speeds, or it could be using, if it's the StreetMap Premium, it has like a more intelligent fallback for, on average, about how much does it take to traverse this edge. Other questions? Yeah.
If you want to know where your barriers are actually located,
yeah.
You have to do a solve with a route, or can you just say where would these have been located if I did a route?
So for point barriers, if you solve, we will tell you where it actually located. And right now, the only way to figure out where it's located is to do the solve. We're thinking about maybe adding a little something in the future. So if you have a use case for that, I would love to know what that use case is.
Well, it's just setting up, people setting up like this road's closed today, the state or local government, and for routing trucks and stuff, they want to see if I click the right point or not, and make sure that feedback to them that here's the actual point that you.
Okay, if like your base map is based, if you have a base map, if you don't, if it's just raw features from the network was built on, it's basically right where you clicked. So whatever the closest physical edge is that's where the point barrier is going to go. Yeah, if you have like a divided freeway with carpool lanes, it gets a little bit more interesting.
That's what I'm saying. So you could like give instant feedback when you click that. Here's where it's actually going to put the barrier.
Right now, we don't have something to do that. You do the solve to get the inputs back. Right now, that would be the only way to do it.
Okay. Yeah, we've heard feedback of trying to understand where things get located. Not necessarily just barriers, but the idea of like, how do I know what my location is without solving it? Right.
Yeah, we're thinking potentially of making another task, which would be a locating task.
Yeah, just where would these?
And you'd feed it a bunch of points in advance and say, here's where they're located for this travel mode, or if they're barrier points, it doesn't matter. And you could look at that information. Other questions?
I have a few, but I'll let Frank decide whether he wants to take them now or offline. You really have an idea what the nature of them are. So I can ask a couple of them now, maybe the ones I think are more.
Yeah.
I was curious about the barriers. You said that they're passed back as result objects.
Yes.
I'm wondering if you can persist those and use them in future contexts or other contexts.
Right now, we don't have a mechanism for persisting them. It's something I've thought about, but right now, no. So they're as long as the object is live in memory, it has that information. If you save the barrier, it would not persist that information. You'd have to rehydrate it the next time you had a solve operation and perform the spatial query.
So the other question related to that is can we have the information or tools to construct our own barriers? So I know the time delay that you're talking about of laying down a polygon barrier, figuring out all the things that it impacts. Do we have a way to kind of pre-create those and just feed them to the solver? Does it just internally is the only way that?
Internally, the only way to do the locating is to feed it to the solver right now. So again, we have considered the possibility of creating a locating task where you could, take all these inputs, barriers or stops, and just say, hey, what's in this thing?
Were you concerned about the locating part of it? Or
just about the time that it takes to actually, really, the use cases, when you have a lot of barriers and the barriers are really big and they're impacting a lot of street segments, I know that's going to be slower than if I just put a point barrier down someplace. And I wouldn't be interested in persisting the output results of a point barrier, but I would be interested in persisting large polygon ones that I know are going to impact my solve time.
In general, I will say that the spatial querying on the SQLite geodatabase is actually pretty quick. And the ability to fetch featured geometries from a query is actually also quite quick. It's faster than, say, compared to like desktop GIS that we write.
The question about the mobile map packages, I'm wondering if that's always something that we have to create new tools, or if there's a here-COTS representation of SMP that comes as a mobile map package as something that we can just buy.
You can absolutely buy it, yeah. And you can buy on, I have like California on my iPhone.
So you could purchase, it's called StreetMap Premium for ArcGIS Runtime.
Okay.
Yeah.
So there's a talk tomorrow. Right. So let's go.
Yeah, Frank's in that talk. He's promised fantastic demos of data products.
I guess this is a question about the size of that data set versus what's in the compressed, like regular SMP that comes in a file GDP. I'm wondering if the US is something that's practical to do it on like a 16 gigabyte iPhone.
No.
I don't think, first of all, I don't think we sell the US. We sell it in regions. And that's 34 gigabytes if you have the US.
Does
We
that-
have a version of it that we don't sell.
Does that include, is that with the geocoding locator or without
That's
it?
with everything.
Okay, so 34 gigabytes.
Locator,
That's Mexico all the way up through Canada. Geocoding and network attributes.
I believe California, being a big state, one of the biggest states, it's 8 gigabytes. A lot of that, I think, is that is a big portion of that is the locator files.
I think it's like half is the locator files. It's pretty significant.
Just a couple more questions.
Yeah.
The curve approach flip that you mentioned, I wasn't aware that was anywhere. Like I know it's not in the BRP, but you mentioned it was in the desktop version of the route solve. So
in,
left-hand side.
yeah, for desktop ArcGIS, you have to, for 10x, you have to go to the properties, enable the don't locate on restricted portions of the network checkbox.
Okay.
It should be there by default.
You think it's in the VRP too?
It's not in the VR, it's not in the solvers, it's in the desktop. How desktop breaks the functionality down is in the locating portion of the software. So when you locate your inputs, it will, I think it's when it flips it then, if I recall correctly.
I think it's in calculate location.
Yeah,
I'm skeptical.
I hope it's there, I wrote it, so. Yeah, so it might not be, so to answer your question in way more specificity, it might be that the OD search is not performing that, but the route search might do it. So I would say though, if it's causing problems for you with VRP, like, let us know. That's probably something we should address.
I'll let Relang.
Yeah. Relang will send it to me. So that's how it works in life. It's fine.
I was wondering, under the route solve, is a route solve a runtime, a multi-objective solve, or a single objective?
Single objective. Yeah, minimization of one impedance attribute.
Is time the default, or is distance the default?
It's up to whatever your default travel mode was for your data or for your service.
It's all based on.
It's based off of the defaults there. If you don't have a travel mode, it's up to whatever impedance attribute was the default in your network data set creation.